let us get started. So last day we discussed how to model the field winding. Then we went on to discuss about the variation of flux linkage of the armature coils with rotor rotation. We have discussed that intensely. That if the field winding is excited with some constant current, and if the rotor is rotated, then because the flux axis, the field winding flux axis, for some rotor position, like for this one, it aligns with, say it aligns with the axis of the coil 1, but it does not align with the axis of some other coils, and it is at perpendicular angle with respect to the axis of coil 4. So you can think, you can understand from here that coil 1 will have the maximum flux linkage, whatever, whether positive or negative, that depends on our sign convention. And coil 4, that will have the least, that will have the zero flux linkage. That you can verify from here also, that at this rotor position, at time equal to t equal to 0, you can see that the pink one, that is coil 4, is having zero flux linkage, and the coil the orange one, that is coil 1, that is having maximum flux linkage, very close to or actually at maximum flux linkage, negative value. So the other one, that is the green one and blue one, they are almost having the same flux linkage. One is positive, another is negative, and their flux linkage values are approximately equal to whatever the flux linkage of the coil 1. So that means if a coil is between this region, say from this point, this angular position to this angular position, we see that because there is almost no flux lines here, from say theta 1 to theta 2, that is why even if the rotor or the rotor, a particular coil moves between this rotor position, there is not any significant change. There is not a significant change in the flux linkage of that coil, but it starts reducing or increasing significantly as soon as it goes under this pole. uh, so that is what we discussed last year. We discussed about these two instances. One is instant 1, that is t equal to 0, for about which I have just told you, and after 90-degree rotation, say at t equal to 10 millisecond, you can see that the orange coil, the coil 1, that has come from horizontal position to vertical position. So at this instant, the flux axis, the axis of the coil 1, is at perpendicular with respect to the field axis. So you can see that the coil 1 in this case, coil 1 at this instant t equal to 10 millisecond, it is having zero flux linkage, and same discussion, and accordingly all the coil flux linkages actually change with rotor position. So if we actually focus on flux linkage of two coils, so coil 1 and coil 4, as indicated by psi 1 and psi 4 in this figure, you can see that they are actually phase shifted. And if we remember that induced EMF in any coil is equal to the rate of change of flux linkage with respect to time, so you can understand that for this coil 1, wherever you have rising portion, there you will have positive flux linkage. So if this is the zero line of induced EMF, between these 2 points you will have positive induced EMF. Wherever you have flat portion, there you will have zero induced EMF, and in the falling region, again you will have negative induced EMF, and again in the flat region you will have zero induced EMF. Similarly, that can be plotted for this coil 4 also. This is the rising portion, you will have positive induced EMF, then zero induced EMF between these two, then some negative induced EMF between these 2 points, again some zero induced EMF between these 2 points, again some positive induced EMF will start and continue like this. So these are the induced EMFs of these two coils. So you can see that the induced EMFs are quasi square in nature. So we discussed what we mean by perfect square. So if this is the time period and this is 2 pi, this is pi. So if a waveform is like this, for 0 to pi it is positive and 0 to minus pi it is same value negative, then that is what we call as perfect square wave. But if it has some zero regions also, then that waveform is called as quasi square wave. So we find that the induced EMFs of the armature coils are in square in nature. They are quasi square in nature. So along with that, if we try to focus on this one, say the coil axis. So say coil axis, say this is dot, this is cross, and in the earlier one this is dot, this is cross. So now the coil 1 axis is vertical, where air gap is quite low, the air gap length is quite low. That means reluctance of the coil 1 at this rotor position is quite low, so inductance is high. But here you can see that the axis is actually horizontal, where you have a large air gap, large air portion, so reluctance of the coil is quite high, so inductance is quite low. So if you see one coils individually, then each coil, the equivalent circuit, you will have to put the small resistance for the winding, then you will have some then you will have some inductance, then you will have some inductance then you will have some inductance and then you will have some induced EMF. So for this is for one coil, so coil say coil 1 equivalent circuit. So this resistance is reasonably constant, this inductance depends on the rotor position, and again this induced EMF, that also induced EMF E1, say E1 depends on the rotor position as well as current, right? So this is the
Sir,
equivalent circuit of a coil. Yeah, go on.
sir, here the inductance will be only due to the excitation of the just field winding, or the current flowing through the armature winding also.
No, inductance is not a function of current. If you ignore saturation, inductance is if you consider any coil, how many number of turns it has, and what is the reluctance of the path it sees. So with rotor rotation, the coil axis actually changes, and along axis it has different air gaps. So that is why the inductance, the self inductance, it is, I'm not talking about the mutual inductance or anything of the coils, it is the self inductance. So the self inductance varies with rotor position. So that is what I told, that if you try to model the equivalent model one coil with its equivalent circuit, then you can see clearly that now this is the rotor position, so this is the coil. You forget what is the excitation, where you have flux lines, you forget all that, but this is the axis. Along this axis you have very small air gap, very narrow air gap. So inductance, self inductance is number of turns square divided by whatever is the reluctance of that path. So this reluctance, you can see that it is quite low, but in the next rotor position if I go, that is 90 degree in the clockwise in the counterclockwise direction, so you can see that the now the axis of the coil has I'm only talking about the coil 1 has shifted like this. So in this portion you have quite a large path through air gap, so reluctance will be quite high. If reluctance is quite high, then the self inductance of the coil, that will be n square by r is quite high, so inductance will be quite low. So that means the coil inductance actually varies with rotor position. So if I talk about only one coil, then that coil inductance, self inductance, will vary with rotor position. And if there is some excitation in the field winding, then there will be some flux linking that coil, and that will change with rotor position. So because of that there will be some induced EMF. That is why this is okay. So this is not the current of its own winding, that is the current of the field winding. I should have mentioned it particularly. So this E1 is actually the current of the field winding. So this E is actually dependent on the mutual inductance between the two coils. So this is actually the mutual inductance between coil 1, that is field winding, and coil 1 into di, or basically the field current into dm d theta. So this is the induced EMF into omega, of course. So this depends on speed also, of course. So this induced EMF basically depends on the speed, the field current, and the rotor position and its expression. So E1 is given d theta into omega, where m is the mutual inductance between the field winding and the coil 1. Does it answer your question?
Yes, sir. But the current, the voltage drop will be due to the current flowing through that particular coil, right?
uh, this voltage will get
Like,
induced. It is not a
yes,
voltage
yes,
drop, it
yes,
will
sir.
be a
E1 is
induced. So
induced.
yes,
Yes,
so
yes,
if
I
you
agree
apply
with it.
KVL,
Uh,
this will act as a voltage. Yeah, this will come in series with that whatever applied voltage you have. So if it is,
yes, yes,
so if this V is higher than E, then current will flow this way, and if it is opposite, then current will flow this way. That is all.
yes, yes. Then the expression for this modeling is R into some current flowing through that particular coil, whereas
Yes.
E1 is just a function of field winding
Yes,
current.
yes, yes, yes. So this is L into di dt, where so I should name, say this is IA. So this is IA into dia dt plus E1, where E1 is this quantity.
Okay, sir, got it. Sir, I have a doubt from the field winding modeling.
Okay.
Sir, in that we have write the express we wrote the expression in the previous slide says VF is equal to IF into R plus L into DIF by dt in the previous class.
Yes.
But
Yes.
IF is DC, right? With respect to time, it is not changing. Then that expression plus after will become zero, I'm thinking.
Yes. Yes. If it reaches steady state, then so this is transient equation. If it is steady state, steady state means the IF is a DC quantity is capital IF, so you will have VF equal to RF into IF. This is the steady state equation. But transient is
Yes.
important, right? When you
Oh,
say you have your winding, this is your field winding, you have some voltage source, now you have some switch, a double pole double throw switch, no, double pole single throw switch. So you turn on, so you have this switch, so you turn on this at some instant t equal to t0, t equal to 0. So then the voltage applied across this winding will see a will be having a step jump, something like this. So obviously the current will not be immediately raised to the, it will take some time. So that modeling will come from here, that will come
yes,
from
sir.
here.
But okay, that's fine. But when some current is flowing through the armature winding, won't it have an induced EMF because of that rate of change of flux, which is due to the current flowing through the armature, sir?
We'll discuss it once we understand how the armature current distribution actually look like.
Okay, sir. Okay, thank you.
Okay. So so here the point that we with what we concluded last class is, here you can see that if I take one armature coil, the inductance is actually varying with rotor position, and the induced EMF that is visible in the armature winding, that is actually a quasi square wave, that is not a constant value. But if we remember what was discussed in our first class on DC machine, even in the steady state, even the steady state equivalent circuit of the armature winding, it was modeled only as some resistance and some induced EMF, say a constant induced EMF, the armature winding. This was the equivalent circuit of the armature winding. And if we include the dynamics, that is the armature inductance, then also it became like that. If we look at some books, or if you have looked at the parameters of any DC machine, typically this resistance is a constant number. There is no confusion in that. This inductance is also a constant number, and this induced EMF is also a constant number. But here we see that if we try to model, if we try to see what happens in one coil, then we see that the coil inductance actually varies with rotor position, and the induced EMF in the coil due to the field winding current is also not a DC quantity, it is a quasi square wave. So the natural question at this point would be, what makes the inductance of the armature winding constant? Or is it reasonable to model the armature winding inductance as a constant value? And is it reasonable, or is it reasonable to model the or what makes it possible to model the induced EMF in the armature winding as a constant DC quantity? So these are the questions at this point of time, and it is not possible to address these questions unless we understand about the winding armature winding. So yesterday we had a brief discussion on armature winding. So we are discussing with this with respect to this machine only. So it has number of slots as 12. It is a two pole machine, and we consider say lap winding, and what else? So it is a say for first case it is a single layer winding. What do we mean by single layer winding? Single layer means if you have one slot, then you have only one coil in one slot, one coil side in one slot. If it is double layer, then you will have two coil sides. So you will have a top coil side, and you will have a bottom coil side in the same slot. So to start with, we will start with the single layer one. We know that there is something called commutator in a DC machine. We will understand what is that, and there is also something called a brush. So the number, we have to decide the number of that. So the rule tells that the number of commutator segments. Okay. So the number of commutator segments is equal to number of coils. Okay, and number of coils is half the number of slots if it is a single layer winding. We understood why. Number of brushes is actually the number of parallel paths of the armature winding. So if it is a two pole machine, we have for lap winding, we know that number of parallel paths is equal to number of poles for lap winding. So number of brushes will also be 2 in this case. And uh, what are commutator, and what is a commutator and what is a brush? So commutator is one cylindrical copper, made of copper material. So something like this. It will obviously have some length along the axis, and so it will be made up of copper, and there will be some insulation between two subsequent segments. So this is whatever we have in between, say this blue shaded one, this whole part is made up of copper, and this one blue part with respect to the next blue part is insulated. These two parts are insulated uh, with some mica or something in between these two segments. So a commutator segment is some cylindrical body like this, where you have these segments. These segments will be like this, and terminals will be coming and shorted with one segment. that is what the connection is like. And the brush is, so commutator is actually mounted on the shaft, so it is rotating with the rotor because the rotor has all the coils, so the coils are also rotating, so the coils will be coming and shorted in some segment. So unless the commutator also rotates, it is not a realizable system. So everything of the coil has to rotate. So the rotor, the coils, coils, this end winding connections, and the commutator, everything is rotating. But we have to take the connection to the external world, that is stationary. So we do that by using some brush. So there will be something here, some say some body which will be pressed. So if I look at the 2D view, if this is the outer surface of the commutator, then there will be some direction like this on two diagonal based on the number of brushes we need to have. Those will be pressing the outer surface of the commutator. So commutator will be rotating, but the brushes are fixed. So we have one terminal coming out from one brush and another terminal of the armature winding coming out from the another terminal. So these form the two terminals of the armature winding which we see externally, and actual windings will get shorted. So we'll see how actual windings will be connected to this commutator segments. And one or two of the segments will be shorted at a instant with this brush. So that we understand that, say this is the say this is one segment, right? How many? 1 2 3 4 5 6 7 8. Here I have made 8 segments. So you can see that at this instant only one segment is shorted with one brush. But if say the commutator actually rotates, and the new segments, basically say this is the new commutator position, then you can see that the insulation, although there is insulation in between, this portion is shorted with this blue one, and this portion is also shorted with this blue brush. So at this shorted with one brush. So again, if it further rotates, it will come back to the original position where one brush will be shorted with one commutator segment. So this is what will keep on happening as the rotor rotates, and along with that the commutator also rotates. So let us try to understand about the single layer armature winding. So first we'll discuss it. We'll discuss how the winding is realized, or how the winding is made. Then for a particular brush position, and what needs to be the brush, where the brush needs to be located for that connection, for a certain rotor position, and with respect to that how the currents will flow. We'll try to look at that. Then we'll move the rotor by little, we'll give the rotor rotate by some amount, so that two commutator segments will be shorted with brush, and then we'll understand how the currents will flow. And then we'll find out that the single layer winding also, it is theoretically it can be discussed, it is not actually practically realized or realizable. Then we'll go for the double layer winding, and we'll discuss the same for that also. So let us get started. So
Sir,
okay,
in case of double layer winding, also number of commutator segments equal to number of coils.
yes, but that will be 12 in that case. So number of
Then
commutator
it will
segments
be,
equal to number of coils. If it is a single layer coil, single layer winding, then you can have only one coil side in one slot. So the number of
yes,
coils you can have is number of slots by 2.
yes,
But if you
yes,
have a double
correct.
layer winding, then you can have two
Num-
coil sides per one slot. So that means the number of coils is equal to the number of slots.
Yes, sir. Correct. Thank you.
Yeah. So let us start. Probably I'll try to make it the rectangular and try to relate with the actual circular one. So what I will do is, suppose that this is the horizontal one and I am spreading the circular one as a rectangular one, and we have the number of, uh, so we have the all. So say, because we have 12 slots here, say this is slot 1, slot 2, slot 3, slot 4, slot 5, 6, 7, 8, 9, 10, 11. Say we'll start from here. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the one we have. So this is the one we have, and say we have some commutator. So uh, how the numbering will go, we'll discuss, we'll come back to it. But we have how many segments we have? Say we have some commutator segments, so it is something like this, and we have six of them. So this is commutator segment number 1, 2, 3, 4, 5, 6, right? So let us make the winding in such a way that some winding will start from segment 1. That means one coil side will be shorted to segment 1, and it will basically go and pass through the slot 1. So this is like this straight one that I am making along the one slot. So that is like that is like the coil length along the axis of the motor, the axial length of the motor. Now because if one side of the coil is at 1, then the other side has to be at the diametrically opposite side, so it has to be at 7, because we have 12 slots here. So it will complete its path like this, something like this, and it will come to 7th slot, and at 7th slot it will come back, and it will actually come and get shorted in the second commutator segment. So this is our first coil. How it will, okay, we'll first complete it. Then let us say we have our second coil. It will start from segment number 2, and it will go to slot number 2. Along slot number 2 it will complete. Then it will have its end winding, and it will have its other side at slot number 8, and it will come back and get shorted at segment number 3. Next, let us take green. So it will start at segment number 3, it will go to slot number 3, then it will, like this, it will go, the other side will be at uh, slot number 9, it will come back and come back here. So next is orange one. So this is where it will start. It will go to the fourth slot, this is the end winding part, and it will go to the 10th slot, the other coil side. It will come back and get shorted at 5. Then the next one, we are left with no other colors, we will again have red color. So this is the next one. So that will go to slot number 5, and it will come back to slot number 11, and it will get shorted to commutator segment number 6. Then we have the next one. This is the one that will go to slot number 6, and the other side will be slot number 12, and it will come back and get shorted to segment number 1 because it's a circular one. So this after 6 will have segment number 1, and it will come and get shorted here. So this is in rectangular one. If I try to do it in the actual circular one, okay, I have done it at rotor position um, rotor position 2. Anyway, it does not matter. So say this is at rotor position 1. Okay, let me complete it and come back. So say this is rotor position 2. So here, say we have to just number something. We'll have to start with something. So let us number this one as 1, slot 1, whatever, say 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the numbers. These are the numbers of the slots. So where do we have the commutator? We have the commutator, say somewhere here. Commutator is like this circular cylindrical hollow cylindrical body. We have 6 of them, 6 of the segments. So all these slots are like, I am representing them with some circles, right? So segment 1 will be somewhere, say segment 1 will just have somewhere, so we have 6 of them. So these are the 6 segments. So this is segment 1, 2, 3, 4, 5, 6. So these are the 6 segments. And now if I try to relate, so some coil will go like this, it will flow at as cross, or that will depend on the current direction. So I'll remain mum about that at this point of time.
Sir, is it lap winding or wave winding, sir?
It is a lap winding.
Oh.
It is a lap winding. Wave winding will not be coming back like this. It will go back somewhere else. Let us limit to lap winding only. So it will go and connect to this slot 1, and it will come back. It will come back from slot 7, and from there, okay, I should have named the commutator one the opposite way, then it is easier to connect. Actually, I should have done that. So 1, 2, 3, 4, 5, 6. So it goes like this, goes all the way, and comes and gets shorted here in the slot number 2. Next, if I uh, go to this coil, the blue coil, that is, it starts from here. Okay, actually I think the earlier nomenclature was only correct, otherwise the flow does not come of the winding. Right, so this is 1, 2, 3, 4, 5, 6. This goes like this, and this has to go back. This whatever is coming from 7, that has to go to coil number 2. So what is a good way to represent the one? It is quite complicated to draw it in the circular one. So
Then
you
I guess
understand that.
if we start numbering from the third as one, uh, the commutator segment which is near
Yeah.
to three third slot may be best one, I guess. From under slot number three, give the commutator segment as one, sir, followed in
So
an
this is one.
anti-clockwise direction.
Okay, let us try to do at rotor position 1. So here afresh. Uh, Actually this rotor is quite small, so it will get complicated. Probably I could have increased the size. If I go back, oh, that will erase this part. So I think for this part, uh, so I think you understand what actually is happening here. So the coil 1, so commutator segment, if I, okay, let us do it. So say this is the commutator. This is the commutator. Say segment 1. That's all. So 1 2 3 4 5 6. That is all. Okay, so these are the segments. Let us start from vertical. 1, then 2 3 4 5 6. So these are the segments. So where can it go very easily? So from, if it is almost at 90 degree, it will be easier, because then it is easier to go and come back. So the coil 1 probably can start like this. It can go here and it can come back like this. Yes, this is what is suitable, I think. So the red coil goes like this. So this is slot 1, this is slot 2, 3 4 5 6 7 8 9 10 11 12. So this is how the slots will have to be numbered. So this is the first coil that goes to slot 1. It comes out from slot 7. It goes to commutator segment 2. Next one, it starts from commutator segment 2. It goes to slot 2. It comes out from slot 8 and it gets shorted at uh, uh, commutator segment 3. Then the next one, it starts from commutator segment 3. It goes to this slot 3. It comes out from slot 9. From slot 9 it has to go to slot number 4. Then it has to come out from slot number 4. It has to go to slot number commutator number 4, to slot number 4. It will come out from slot number 10 and it will go and get connected to slot number commutator number 5. Then again the red one, it will start from uh, commutator number 5. It will go all the way to commutator slot number 5. From 5 it will come back from 11 and it will get shorted to slot number 6. Again blue one, from 6 it will go to slot number 6. It will come back from slot number 12 and it will go and short to slot number commutator segment number 1. So this is how the actual winding would look like. So only one for giving you reference how it would look like. I am drawing this. It will be quite complicated to draw it all the time. Just to explain to you that yes, this is the circular one. So actually, if it completes one rotation, then the next one will actually come after 6. It will be 1. Okay. So fine. Now for this rotor position you can understand, so where the brush should be. Actually for this rotor position the brush should be uh, between the brush should be between 1 and 2. It will be shorting 1 and 2, and the other brush has to be, why you will understand, the other brush will have to be between 4 and 5. Okay. So obviously so it is shorted to 1 also. So we'll stop at this point and we'll go back to rotor position 1, because that is more obvious uh, why the brush position has to be the way that I'll indicate. So for this rotor position we have the same winding. I'll quickly draw that so that we have ready reference. 5, 6, 7, 8, 9, 10, 12. So these are the 12 slots. And we have the armature, we have the commutator segments 1, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, and again 1. So this is how it will go. The first one will come back from 7, it will come back to 2. Second one, it will start from 2, go to coil 2, go like this, come back from 8. Next one, green one, start from slot 3, go to coil 3, come back from slot 9, and again get shorted to commutator 4. The next one, start from commutator 4, go to slot 4, come back like this from slot number 10, get shorted at commutator 5, then start from 5, go to 5th slot, come back from 11th slot and short it to 6. Then the next one, start from 6, go to 6th slot, come back from 12th one, come back and get shorted to 1. Back to that one. Now we understand that from our understanding of the operation, that we need to have positive current or current of same polarity under one pole. So that is the requirement. We understood from DC machine principle that if we have, hypothetically, if we have all the dot currents under one pole and all the cross currents under the other pole, then it is possible for us to get a stationary armature magnetic field, and that will produce some torque. So for that where the brush should be, that is the question. So let me number the coils like this. So say how to number, okay, we can number anything actually, 1, 2, 3, 4, it does not matter that way. So let us assume the brush to be at, so let us first assume the brush location, then we will come back to the coil numbering. So let us assume the brush is perfectly touching commutator segment number 1 and it is touching commutator segment number 4. So 1 means that 1 will come to here also. So these two are the same ones. So These and this, they are the same terminals, and this is the other terminal. So if again I should indicate this to be the same terminal, and this is the other terminal. So in total these are the two terminals coming out. So let us assume that let us assume some current direction, say from this one some current I is going, and that whole current has to come back, from this terminal. So terminal A and terminal B. From terminal A all the current is going in, and terminal B all the current has to come out. So let us understand how the current path will be. So this current will go like this. So this current will flow through coil 1 in this direction. It will follow the red one and flow from slot 7 like this in the opposite direction. It will come to commutator 2. From commutator 2 will get shorted. These are internally shorted, so current will go to coil 2. It will flow like this through the blue one, and it will come back from the blue other slot 8 like this. Then again it will come to commutator 3. It will get shorted to the commutator segment 3. It will go and flow like this through the green one. It will complete its path to the green one and come back from slot number 9, and it will come and it will flow. So from here, say I was going I by 2 went in this path, and another I by 2 has to go the other way. So I by 2 has actually come, and I by 2 has returned. So this is I by 2. Now the other I by 2 will have to start from this one, the other terminal will have to start. So this I by 2 will go like this, and it will flow from this blue one, complete its path like this. It will come back here, it will short internally, then through this other red one it will go on the top direction. It will come back in the downward direction. It will again get shorted at commutator number 5. It will go in the upward direction like this, and it will come back in the downward direction like this. Here it will complete its path, and the other component, other I by 2 is also coming back, and this makes this total I. So this is how the currents would look like if the brush positions are like this. Now we understand that for this given rotor position, all the top conductors will have to carry current in a certain direction, and all the other ones have to carry current in the other direction. So we can name them accordingly. So let us say 1 2 3. If we try naming it from here, 3 4 5 6 7 8 9 10 11 12. So let us name them like this. So say dot or going up, that indicates a cross. So it is cross here, cross at 2, cross at 3. At 4 it is the opposite way, so it will be dot here. 4 5 6 7 8 9 all are basically same polarity, and again 10 it will be of the first polarity, that is cross. 11 same polarity, 12 same polarity. So this is how the current directions are for this rotor position if the brushes are at this location. So that means if we have to we have to if we want to have current polarities like this, all cross in on top and all dot at the bottom, then our brush connection at that rotor position should be like this. Our brush location has to be somewhere here. Actually brush location is fixed, but the commutator as well as the rotor will rotate. So if we now try to draw the circular commutator also here, so how will it be? So maybe it will be um, The actual brush may be somewhere here, so that, so this is the segment 1. From there it goes, it comes back. So this is how the segments are. So this is the actual brush location, let us say, and it is touching segment 1, and the other other brush is touching segment number 4, and in between we have these segments which are not touched, which just acts as the shorting path for the winding. Now let us go back to rotor position 1. So what happens if we move by some small angle, so that now the brush is actually touching two commutator segments rather than one. So again, mind you, the commutator and rotor are the one that rotates. The brush and the stator field that remain the same. So at this rotor position, which coil is having the maximum? So at this rotor position, for this winding connection, what is the induced EMF? Let us try to see which all coils are having induced EMFs. So the red coil between slot 1 and 7, let us try to see for this rotor position. So we are discussing which rotor position, some position like this, where coil 1 is here. So it is close to this point. So that, as at t equal to 10 millisecond, where the coil 1 is here, actually it would be somewhere here, little ahead from that, where the coil 1 has actually come to this rotor position. That is the instant we are discussing. At that instant, you can see that the red one is having positive slope, the blue one is having positive slope, the green one is having negative slope, the brown one is having negative slope, and the others are having zero slopes. So you have coil 1, so you have coil 1 giving some positive voltage, coil 2 again giving some positive voltage, coil 3 it is approximately 0 voltage, coil 4 again 0 voltage, coil 5 and coil 6, coil 5 is brown, so it is negative voltage, and coil this green one, coil 6, that is also negative voltage. So if I put the polarities here, let me use green. So coil 1, say this is positive voltage between these two terminals. So this terminal to this terminal, it is having some positive voltage. The blue one is coil 2, that is also having some positive voltage. So this to this is again some positive voltage. Now the green one, or the coil 3, so now the color does not match. Coil 3 is having 0 voltage. So coil 3 is like there is no voltage across it. Coil 4 also there is no voltage across it, and coil 5 and coil 6 are actually having negative voltage. So coil 5, where does it start? I think it is better to indicate the polarities here rather than at the bottom. There it will get complicated. So this is, say, for coil 1, the other terminal, this is like this. So this is coil 1 voltage, coil 2 voltage is like this, coil 3 does not have any voltage, coil 4 does not have any voltage, coil 5 it has opposite voltage, and coil 6 again it has same polarity as that of coil 5. Where is coil 6? Yes. Now let us see what is the voltage, total voltage, or how does these voltages, individual coil voltages, add up or they get subtracted. We'll try to follow the path and try to see. So let us follow this I by 2 path from here. So here E gets added and again E gets added for coil 1, and coil 1 and coil 2 voltage, you can see these two are additive in nature. Coil 3 does not have any voltage and it ends its path. Right, now we'll have to start from coil the other I by 2. Other I by 2, if we see, this current path is again opposed by this induced voltage, so here also it will get added, and again this also it will get added, the induced EMF, and again coil 5 voltage, that will also get added, and again coil 4 that does not have any induced EMF. So if I try to draw the equivalent circuit diagram, let us draw only the induced EMFs. So say this is the total current I, from there this is I by 2 flowing, this is another I by 2 flowing. In this path, first the induced EMF for the coil 1, then induced EMF for coil 2, then coil 3 is like a short, so it goes and completes its path like this. Now the other path, it is the induced EMF of coil 6, then induced EMF of coil 5, then coil 4 is a short, and it goes back like this. So you can see what do we mean by parallel path here. Here there are two parallel paths for current, and we have these induced voltages coming, some induced voltages coming in series. So here in this case we have two induced EMF. So if one so say this induced EMF is say 100 volt, and again the other one, all the induced EMFs will be of same magnitude only wherever they are positive or negative. So say this is 100 volt, this is 100 volt, so the total induced EMF will be 200 volt, and the same thing will come in parallel. So the total net induced EMF is equal to 200 volt in this case, because we have two coils which are having non-zero induced EMFs, and in a path of the two parallel paths, and they are connected in parallel. So that is why the net induced EMF will be the summation of induced EMFs of two coils at that instant. That comes out to be 200 volt if we consider one to be 100. Is there any confusion here? I'll stop here to for questions. Anything?
Sir, will there won't be any change in the magnitude of the induced EMFs?
Is there any?
I'm
What do
thinking
you
that
think
the
about the
magnet.
what do you
I'm
think about the
thinking that
slopes of these ones?
slopes are same, sir.
So induced EMF is same as the slope. So
Okay,
wherever the
but
induced EMFs are positive or negative, they are of the same magnitude.
correct, but they are displaced, right?
Yes, but the entire waveform, that is what I indicated here, right? So this slope is same as this slope. So this 100 volt and this 100 volt, they are in magnitude they are the same. So in current, so so the amplitude, so the magnitude of this voltage, that is the same. That is, we are not discussing of a, it is not a sinusoidal quantity, it is a quasi square wave with a flat DC value. So for some time
Yes, sir.
duration this voltage will be constant, so we can simply add them.
Yes, sir. Sir, could you please go to that displaced waveform once?
This one,
Yes, sir. Yes, yes.
yeah,
Suppose we are at around 2 milliseconds. Suppose we think at
2
that instant
milliseconds,
of time. Yes, sir.
2
Yes.
milliseconds.
At the
So
instant.
5,
Yes, sir.
1 2 3 4 5, so 2 millisecond, yes,
Yes.
this
At 2
instant,
millisecond. Ah, yes, sir. Exactly.
yes.
at that instant, in the coil 1 we are having zero flux linkage, zero EMF, right?
Zero EMF.
At the same instant of time we are having 100 volts here.
In coil 4,
At that,
yes.
yes, at that rotor position, the EMFs are not same, right?
EMFs, so these two EMFs will come in series. So let us go to the complete picture, say here. Okay, if you are talking about say 2 milliseconds, say
Yes.
this is 5, 2, 3, 4, 5. So this is 2 milliseconds, right?
Yes, sir.
So the
Yes.
coil 1 will give zero induced EMF.
Correct.
Coil 2 will have some positive induced EMF. Coil 3 will have some positive induced EMF. Coil 4 again will give some positive induced EMF, and coil 5 will have some positive induced EMF, and coil 6 will have some zero induced EMF. That is correct.
Correct.
Now if we position the brush for this rotor position, and if we see the equivalent circuit, the current path basically, then we'll be able to see that two of these same induced EMFs will come in series, something like this, and another coil will also come in that path, but that is short, that is zero induced EMF. So this will form one path, one of the parallel paths, and the other one will be something like this. Again, the third coil will be shorted, so this will become the equivalent circuit of the armature. So again you will find that it will be there will be two coils in series with non-zero EMF which will get added. So again you will have 200 volts if one coil the voltage is 100 volt.
Okay, sir. Sir, one more
Okay.
thing, sir. Could you please provide us with an intuition how the wave winding would be, so that we'll have a picture about it?
Wave winding is some other winding pattern. So it is the same winding. So only I have discussed the winding is coming like this. Wave winding will not, the same winding terminal may not come here. It will go somewhere else. That is all. So
Okay,
only the winding
sir.
pattern will be different, nothing else.
Actually, what my point is actually,
Yeah, come.
okay,
What is your
but
point?
lap, uh, at least that point once, please.
Position 1.
Uh, Sir, my question is like, why this winding is named as lap? Is there any specific reason?
I am not aware of that.
Okay, okay, sir.
Name givers, they
Actually,
have
I
named
don't get a
something, I don't
picture.
know.
Okay, okay, sir. Actually, I don't get a picture of what is lap and what is wave. I continuously confuse among these, and I don't have a clear picture. That's why I'm asking.
Nomenclature, why that name is lab, I am also not aware. But yeah, you can find there is some fundamental difference in how you connect the, if one terminal goes like this one will come and connect to the next commutator segment. For wave winding it will not be like that, it will go somewhere else. That is the only difference. That is all. If we
Okay,
understand
sir.
one, our we are not discussing about machine design, we are discussing why induced EMF is a constant number, although different induced EMFs are quasi wave nature, but what makes the induced EMF constant for a rotor position, that is what we are discussing, right? So I think at
Okay,
this
sir.
at this rotor position at least you get that, yeah, the voltages are coming in series and they are also coming in parallel, so that makes it constant at least for this rotor position. We are yet to discuss
Yes,
the
sir. Yes.
next rotor position.
Yes,
So
sir, I
let us
got.
discuss about this position 2, where the two nearby segments they are basically shorted by the brush location, right? So I'll erase the earlier whatever circular ones I had drawn. That led to confusion, nothing else than that. So yes, so can you observe what is happening here? You can see that the coil 1, okay, let us name the coils. So which what are the names that we used? We used coil 1 to be here. So earlier coil 1 was here. So this is our coil 1, 2, 3, 4, 5. This was our rotor coil slots. Now it has moved little bit in the anti-clockwise direction. So this one will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the ones. These are the slot numbers. Now which one will have maximum induced EMF? Which coil? The coil which is directly under the pole. That is the sixth coil. Sixth coil, the one side, another side. Which coil will have the minimum or zero induced EMF? Obviously, this one will have
3.
zero induced EMF. Coil 3 will have zero induced EMF. Is it correct? The brush location or the namings of the coils, are they correct? Because 1, 2, 3, 4, 5, 6, 7, 8, that is fine. And 6, yes, that is correct. So 6 is where? 6 is this blue one, right? 6 is this blue one. Okay, let us continue. So at this rotor position, you can see that coil 3 is having the maximum induced EMF, and coil 3 is having the zero induced EMF, and coil 6 is having the maximum induced EMF. Now what is happening here? What is happening? So here you can see that coil 1 is shorted. Coil 1, can you see that? Coil 1, this terminal and this terminal, these two are shorted by this brush. But coil 1
Yes,
is
sir. Yes.
having actually I think I have named it incorrectly. The not here, I'm talking about rotor position 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 are the 6 coils, 12 coil sides. You can see that the red one, this terminal, commutator segment 1 and commutator segment 2, they are getting shorted, but this coil actually has the maximum EMF. If you look at the other coil that is getting shorted is actually the coil 4. The coil 4, the orange one, that is getting shorted because five the 4 and 5 commutator segments, they are getting shorted by this brush. So that is okay. Coil 4 is anyway having zero induced EMF. So even if they get
Yes.
shorted, it does not matter. But coil
Yes.
1, it is having maximum induced EMF. But still, for the single layer winding, they are getting shorted. So that is something
Yes.
that is not
Not.
desirable. So
Yes.
that is why actually the single layer winding, although we can make some winding and operate it ideally, but because in this intermediate brush position actually the coil which is having maximum induced EMF, that gets shorted by the brush.
Yes.
So single layer winding is
It's
never
not
actually
desired.
used practically. It is never used
Okay.
practically. So
Okay.
next we have to go to double layer winding, and there we will be able to see that if we actually employ double layer winding, this problem does not come. But so because it is not a practical one, let us not waste time discussing how the current flow will be. We'll start with the double layer winding for this rotor position 1 on the next day,
Okay.
and we'll solve it. So that day we will discuss the current direction for this rotor position 1 as well as rotor position 2. So that will make it absolutely clear, and you can think that you can understand that if it moves further, actually it will come back to this first rotor position only, and you will realize how things are how what will happen that time. So probably we'll discuss about rotor position 1, 2 and another rotor position 3, where say this is say coil 1, some coil, what was the name, this was coil 3. So we are discussing about coil 3. Coil 3 after some rotation comes here. Now again after some rotation it will come here. So when coil 3 was here, so at some time this was coil 3, after some time this became coil 3, and after again some time this became coil 3. So if I look at coil 3 current, say I3 with time, when the coil 3 was at this rotor position, or from this rotor position to this rotor position, from this portion to all the way to this portion, it was always positive current. When it became came to here, then the current ideally should be 0, and when again it comes here, we'll see that the current will become opposite polarity, so it will come back here. So in between, whichever coil passes through this magnetic neutral axis, that is the quadrature axis, if this is the direct axis or flux axis 90 degree to that coil actually goes through something called as commutation. That means the current polarity becomes opposite, and during current polarity becoming opposite, it is desirable that that coil will be shorted by the brushes, the two terminals of the coil, uh, they will be connected to two nearby commutator
Shorted.
segments, say coil 3 and commutator segment 3 and coil segment 4, and they will get shorted by the brush.
Okay.
So it is ideally desirable that these two coils, or that coil, should have zero induced EMF at that position.
Okay.
That is all. Okay, so we'll
Okay,
start
sir.
with double layer winding next day. Any question
Sir,
at this point of time? Yeah.
yes, sir. Sir, though the induced EMF is a quasi square wave,
Yes.
but the current is continuous, right?
Because which case do you want to discuss? It is the motor or generator or both?
Actually, we are going. Actually, in one of the lectures, sir, we have some figure regarding the current and the voltages. I guess in the last class, I guess,
Current
which
and
you have,
voltages.
yes, sir, yes, you have drew it. Um
What
Actually, in the
current and
displaced
voltages?
one, I guess. In displaced waveforms, you have shown, sir.
This one.
Yes, 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 sir.
Okay.
I guess in
Anyway,
the
that
pre.
that we'll discuss later when it comes. Current actually
Oh,
will become clear when we understand.
yes,
So
sir.
when we understand what is the equivalent circuit of the armature winding plus commutator plus brush.
Yes,
Okay, so there all the some of the coils will come in series, some of the coils will come in parallel. It will it will be some. So if one coil we represented like this, right? Some resistance, some inductance, plus some sorry, plus some induced EMF.
yes.
That is varying. That is dependent on field current. That is dependent on rotor position,
Speed,
rotor
yeah,
speed,
and speed,
and uh,
angular position.
rotor position obviously, yes. That is speed, rotor position, and field current. Now we will see that because of the commutator, if we try to look at the coils plus commutator plus brush, so we have some system, some armature winding. We are looking at just two terminals, right? And inside this is the model for armature coils plus commutator plus brushes. This becomes the model. Then as we discussed, because of the placement of the brushes and the connection of the coils to the commutator winding, we'll find that, say, this is one coil model, this is another coil model, this is another coil model. Say they are coming, uh, so these three are coming in series, and we have another parallel path. These three coils are coming in parallel, and they come and close the path like this. So it becomes the equivalent circuit of the complete armature for at least one rotor position.
Yes, sir.
Now we
Yes,
saw, we
exactly.
understood that the inductances, the induced EMFs, this
Will
induced
be
EMF may
quasi
be
square
something.
wave.
Yeah, this induced EMF, if we look at individually, will be quasi square wave. Individually
Yes,
looked at, this induced EMF will be quasi square wave. Individually this will be quasi square wave. Similarly, all the ones will be quasi square wave if individually they are looked at. But if we at any instant of time, if we go instant by instant and see and get the equivalent induced EMF for the circuit, then we'll find out that if we try to model the entire thing, then it could be perfectly modeled with some constant resistance, some constant inductance, and uh, some constant induced EMF. That is only dependent on speed. That is all. The series or parallel combination of these, or of these individual coils, will lead to this. Okay,
focus.
so let us stop.
Thank you, sir.